So we have this number C of n comma k, which is the number of subsets of size k in a set of size n. And we want to prove if k is a positive integer between 1 and n, then C of nk is C of n minus 1 k minus 1 plus C of n minus 1k. So just for fun, let's just check an example of this. Suppose we let n equal 3 and k equal 2. So what is C of 3, 2? This is the number of subsets of size 3 from a set of size 2. So if we had the set 1, 2, 3, the subsets of size 2 are 1, 2, 1, 3, and 2, 3. So the number of two-element subsets in a set of size 3 is equal to 3. What is C of n minus 1, k minus 1? 2, 1. This means you have a set of size 2. And what are the one-element subsets? 1 and 2. So this is equal to 2. What is C of n minus 1k, 2 comma 2? If you have a set of size 2, there's only one subset of size 2. So C of 2 comma 2 is equal to 1. And what this formula says is 3 equals 2 plus 1. So that's reassuring. It looks like might be true. And I'm going to prove the general statement, this formula, give it a star, by thinking and not using mathematical induction. So here is the proof. So divide the subsets. So we have a set with n elements. Divide the subsets of size k into two classes, two different sets, into two groups. So let's suppose that our set X consists of the elements from 1 up to n. And we can have, let's call it group 1. These are the subsets that contain, the subset, I'll call this group, yeah, all right. This group 1, the subsets that contain the number n, and group 2 are the subsets that do not contain n. So the problem is what? We have a set of size n. We want to count the number of subsets that contain exactly k elements. And we can divide them into two groups. We can take one of the elements, say n, and look at all the sets that contain n. And group 2 is all the subsets that do not contain n. And then we make the following observation. If A is a subset of X and n is in A, and the cardinality, the size of A, is equal to K, then what can we say about A? A is equal to N together with some other set A prime, where A prime has K minus 1 elements, and A prime is contained in the numbers from 1 up to N minus 1. Right? So all this is saying is, let's say we take N equal 10, and we look at all the subsets of 1 to 10 that have 4 numbers in them. Some of them contain the number 10, some don't. If the number does contain the number 10 and it has 4 elements, then it has 3 other elements between 1 and 9. So the number of sets that contain the number n and have exactly k elements is exactly the same as the number of subsets of the first n minus 1 integers that have k minus 1. So the number of sets in group 1 is exactly the number of ways you can choose k minus 1 elements from a set of size n minus 1. That's the number of sets in group 1. What about the sets in group 2? If A is a subset of X, and this number n is not in A, that's what the symbol means, n is not an element of the subset A, then A is in fact a subset of the first n minus 1 elements, because it doesn't contain n. So the number of sets in group 2 is the number of ways you can choose from a set of n minus 1 elements, a subset with exactly k elements. So the answer we're looking for, how many sets are there of size k in a set of size n, is the number in group 1 plus the number in group 2, that's c of n minus 1, k minus 1, plus c of n minus 1k. And that's the proof. Any questions about that? I mean, this is something you need to think about a little bit, because this is what you do in algebra or throughout mathematics. You have to reason, you have to think about how you prove something rigorously. And this is a nice example of a proof. So to think of this originally is pretty hard. But studying and learning proofs, eventually you figure out how to do things like this. So problem. So we have X, a set with the cardinality of X equal to n. We know that P of X, which is what is called the power set of X. So this is the set of all subsets of X. So for example, if X has 1 element, let's say X is just the set consisting of the number 1, what are the subsets? The empty set and the set with 1 element. So altogether, the cardinality of this power set is 2. We have 2 subsets, 2 to the power 1. And how many have an even number of elements? Well, this has 1 element. 1's an odd number. This has 0 elements, and 0 is an even number. So let's say, so the number of subsets with an even number of elements is 1, which is 2. In this case, n is equal to 1, 2 to the n minus 1. Let's look at another example. Suppose x has 2 elements. So x is the set 1 and 2. So what are the sets with an even number of elements? Well, you have the empty set and the whole set. And what are the subsets with an odd number? Well, just the 1 element sets. So the number of elements, the number of subsets that have an even cardinality or even size, there are 2 of them, which is 2 to the n minus 1. When n is 2, n minus 1 is 1, 2 to the 1 is 2. Oh, that's a good start. Suppose we take x to be a set with 3 elements. So if a set has at most 3 elements, an even number, a subset with an even number of elements has either 0 or 2 elements. The only set with a 0 number of elements is the empty set. And then we have 3 2-element sets. So the total number of even element sets is 4, which is 2 to the 3 minus 1. So that's reassuring. It somehow is giving us evidence this might be true. Let's do one more example. Suppose x has 4 elements in it, 1, 2, 3, and 4. So a subset that has even cardinality has either 0, 2, or 4 elements. So the subsets with 0 elements, the empty set. The only subset with 4 elements is the whole set. But what about the 2-element sets? We have 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. So altogether, the number of subsets with an even number of elements, 3 plus 3 plus 2, is 8, which is 2 to the 4 minus 1. So in all of these cases, it looks like what we need to prove might actually be true. That's always a good thing. So let's see if we can figure out a way to prove it. So we want to prove number of subsets of with an even number of elements if the cardinality of x is n, then this number is the answer, 2 to the n minus 1, half of all the sets. Well, let's see. Any suggestions about how we might prove it?
I did it by induction, and
Yes.
I divided. So we already did the base case, and now we're going to assume that it works for n, and then prove n plus 1. So we're going to say the cardinality of x is equal to n plus 1. So then we need to prove that it's equal to 2 to the n.
Okay.
The number of even sets is equal to 2 to the n. So I divided the sets into, let's call it x prime with a, an additional element, which would be the n plus 1, where the cardinality of x prime is n. And for that, we know there are 2 to the n minus 1 subsets with even number of elements. And as you proved in the previous lecture on the video, there are a total of 2 to the n subsets. So there must be 2 to the n minus 1 odd subsets as well. So take all those odd subsets and put the new element a into it, and that's an additional even subset. So you have 2 to the n minus 1 plus 2 to the n minus 1, which gives you 2 to the n.
Oh, excellent. That's perfect. Perfect. Are there questions about that, or should I just go through it again just to make it a little bit more clear?
Yes, please.
All right, so this is exactly, who's that? Was that Rebecca who gave that answer?
Yes.
All right, so this is Rebecca's proof, and the proof is by induction on n. So we already checked it's true for n equal to 1. So assume the statement is true for some integer n greater than or equal to 1, and we must prove this is true for n plus 1. So suppose X is a set with n plus 1 elements. For simplicity, I'll just assume it's the numbers from 1 to n plus 1. And we divide the even subsets into 2 groups. In the first group, called subset A, n plus 1 is in A. And in the second group, n plus 1 is not in A. So if n plus 1 is in A, then if I take A and remove the element n plus 1, I'll call that A prime. This is a subset of 1 up to n, and A prime is odd, because if you take an even number and you subtract 1, you get an odd number. So if A prime has an even number of elements and one of them is n plus 1, and you look at all the others, you have 1 fewer, an odd number. And by the induction hypothesis, if you have 2 to the n minus 1 even sets, you have 2 to the n minus 1 odd sets. So the total number of sets with this property is 2 to the n minus 1. So there are 2 to the n minus 1 even subsets that contain n plus 1. But what if n plus 1 is not an element of the subset? In that case, so this implies that the subset is actually contained in the integers from 1 to n, and A is even. And by the induction hypothesis, the number of even subsets of a set of size n is 2 to the n minus 1. So we've taken all the even subsets of a set of size n plus 1, divided them into 2 disjoint groups, 2 groups that have no elements in common. One group has 2 to the n minus 1 elements. The other group has 2 to the n minus 1 elements. So the total number of even sets is equal to 2 to the n minus 1 plus 2 to the n minus 1, which is 2 to the n, which is 2 to the n plus 1 minus 1. And that's exactly what we wanted to prove. So that's lovely. That's a very nice proof. So we have the following problem. Let C naught be the set of all integers. Z is the standard notation for the set of all integers, such that
3n.
3 divides n, or let me call this capital N. 3
They wrote it
divides n.
3n such that n is an integer.
Right. or n is equal to 3 times n for some n. And C1, so I can just call this the set of all 3n, where n is an integer. C1 is every number you can write in the form 3n plus 1, where n is an integer. And C2 is all numbers you can write 3n plus 2, where n is an integer. So what we have to do is remember what they taught you in elementary school. If you divide a number n by 3, you get a remainder of 0, 1, or 2. So every number is of the form 3 times something n plus a remainder. R is 0, 1, or 2. Right? Take an integer, you divide it by 3, you get a remainder. And this way of writing a number is unique. So that's the proof. If you want a slightly a different kind of proof, you want to show that these 3 sets have no elements in common. So suppose you have a number n, which you can write as 3n1 plus r1. R1 is always 0, 1, or 2. And you have another way to write this number as 3n1 plus r2. Well, r2 is also between 0, 1, and 2. And what we want to show is that r1 equals r2. Well, how can we show that? Well, let's look at these equations. You have n is 3n1 plus r1 is, call this n2, different quotient. There's also 3n2 plus r2. If we arrange that, we get r1 minus r2 is 3n2 minus n1. So therefore, 3 divides r1 minus r2. But look at this. If r1 and r2 are in 0, 1, and 2, the difference between r1 and r2 is at most 2. And if you have an integer, which is a size at most 2, and it's divisible by 3, that means r1 has to equal to, r1 minus r2 equals 0. So r1 equals r2. So if I have a number n, which I can write as 3n1 plus r1 and 3n2 plus r2, these are the remainders. The remainders have to be the same. And these sets, C0, C1, and C2, these are exactly, this is the set of all numbers that leave a remainder of 0 when you divide by 3. These are the integers that have a remainder of 1 when you divide by 3. These numbers have a remainder of 2 when you divide by 3. So that's the story. These numbers can't have, these 3 sets are pairwise disjoint. No number can belong to 2 of them simultaneously. But we also know from elementary school, when they taught you to divide, if you take a number and divide by 3, you always get a remainder of 0, 1, or 2. So every number belongs to one of these sets, and every number therefore belongs to a unique one of these sets. And that's the little proof.